Okay, suppose f maps from R to R. Let the absolute value of f of x be less than or equal to the absolute value of x to the 4 for all values of x in R. And we're required to show that f dash of 0 is equal to 0. So how are we going to go about this? First, going to write out f of x and expand out the absolute value. So obviously, absolute value of x to the 4, we can bring the 4 inside of the absolute value. And same on the other side. From here, we are essentially required to show that the first derivative of at the point x equals 0 is equal to 0 for this function x to the 4. So if you know that x to the 4, if we draw x to the 4 real quick, it's more or less a parabola centered at the origin, and the absolute value of that just is this. So it's like x squared, but a little bit more flat at the bottom, but at the same time a little bit more steep. So something like this. So we're required to show that the gradient at the origin, essentially, is flat. Okay, so it's not obvious just yet, but let's try and see why this is the case. So applying our first derivative, first principles of differentiation, we can apply that. We know that f dash of x is equal to the limit as h goes to 0 of f of x plus h minus f of x, all on h. So once we prove this function, this holds true, we can essentially do the same thing and apply that this will still hold at x equals 0. And so in this case, f of 0 plus h minus f of 0 over h, this should equal 0 for our function. Cool. So the way we're going to go about this, we're going to apply this derivative operator to both sides of this inequality. So f dash of x plus h minus f of x in absolute values all over h is less than or equal to f of x plus h minus f of x all over h is less than or equal to the absolute value of f of x plus h minus f of x all on h. Cool. And from here we can show now that the limit as h goes to 0 will approach this f dash of x. Okay, so let's apply the limit to each of these terms as h goes to 0 of absolute value of f of x plus h minus f of x, maintaining that minus sign, is less than or equal to the limit h goes to 0 of f of x plus h minus f of x all over h is less than or equal to the limit as h goes to 0 of f of x plus h minus f of x. Cool. So now we can see that this is actually less than or equal to the f dash of x. Cool. And this would just be obviously for the left-hand side derivative in the right-hand side derivative case. Okay, so we can, now what we can do, we can in fact sub in our x equals 0 term, and let's write this whole thing out like that. So f of, okay, so we can write our function in. So our function was minus x, so 0 plus h to the power of 4 is less than 0 to the power of 4, well now it's plus, over h. And the same thing on the other side, so 0 plus h to the power of 4 minus 0 to the power of 4 all over h. And now we can, with the limit sign here as well, still need to maintain the limit. And now we can simplify this a little further and say that the limit as h goes to 0 from the negative direction is h to the 4 on h is less than or equal to f dash of 0 is less than or equal to limit h goes to 0 from the positive side of h on 4 on h. And now we can simplify this even further. And this becomes h to the minus 3. Still maintaining the absolute value signs. Cool. And now, subbing in our 0, we get minus 0 to the 3 is less than or equal to f dash of 0 of 0 to the 3. And obviously by the squeeze theorem, so the squeeze theorem says that if we have a function of g of x is less than h of x is less than f of x, and the limits of f and g converge to, say, 0, then h must also converge to 0. Cool. So applying this, we get that f dash of 0 equals 0. Cool.